Lesson number 8, surface area and volume of pyramids and cones. So to define a pyramid, when we defined a prism, we said that a prism had a flat bottom and a flat top. Or it has a polygon, a quadrilateral, a hexagon, a triangle, and then it has these lateral faces that are rectangles. The exception being a cube like this one where they're all squares. Well, in a pyramid has one base, which means that everything meets at a point, either at the top or it could be at the bottom if I flip it over. And the lateral faces this time, instead of being rectangles, are now triangles. So when I'm looking at a pyramid, there's a couple of measurements I have to be careful of. There's the height of the pyramid. The height of the pyramid is defined as the distance from the tip straight down to the base. It falls in the middle of the base. So it's the vertical height of how tall my pyramid is. Then there's the slant height. The slant height is from the tip, or we call the apex of the pyramid, to the middle of the base, going down the side length. This is actually the height of my triangle. So this is the height of my triangular faces, whereas the H is the height of the pyramid itself. Now, what do I have here? I have a pyramid that fits exactly inside a prism. And we're going to use this to indicate a couple of the measurements. So when we're dealing with pyramids, we have two measurements. We have surface area and we have volume. Surface area, same as how we did the prisms. Find the area of all of the faces. I have 4 triangles and I have a base. In this case, my base is a square, which means all 4 of my faces are going to be the same size. That doesn't always happen. Sometimes I might have a rectangular base or I might have a triangular base, so my faces might not all be the same. I have to be careful and I have to watch for that. I also need to make sure that my slant height is going to be the proper slant height, that it is the height of the triangular face, and that the height of the prism is my H. That's surface area. Now let's get into volume. So to get into volume, I have a demonstration for you. Because I can fit this prism and this pyramid together. So maybe there's a relationship between the two. Well, let's see what happens. If I take my pyramid and fill it up with water, because remember, volume is capacity. So this is how much water it holds. So that's virtually full. So when I fill it up, let's mark the level. That was one pyramid. Fill this up again. A little bit of a dribble on the desk, not bad. This is 2 pyramids. How many pyramids can I fit into the prism? If your answer is 3, you were probably right. So what relationship did we discover with this? Well, we discovered that 3 pyramids equals 1 prism, so then 1 pyramid would be equal to 1/3 of the prism. So how does the volume of a pyramid compare to the volume of a prism with an identical base and a height? The volume of a pyramid is 1/3 the volume of the prism. And when I'm saying that, I'm meaning that as long as the bases are the same and the heights are the same. The bases of my prism and pyramid were the same, because look, they fit on top of each other, and the height was the same. Next demonstration. What do I have here? I have a cylinder and I have a cone. We did cylinders last week. The surface area of a cylinder was the two circles and then that curved part. The volume of my cylinder was the area of the base, which is circle times the height. Cones are a bit different. So when I'm dealing with a cone, I have a circle. So I'm going to find the area of the circle when I'm doing surface area. And then I have this curved part. Now this curved part, there is a proof for it, but the proof is really out of our league in grade 10. But what it comes down to, it is pi times r times s. S refers to the slant height. So if you remember in a pyramid, my slant height was from the apex to the base going along the edge or the side of the cone or of the pyramid. Slant height is the same way in a cone. Slant height is this measurement. Height is the measurement that goes from the apex to the center. So it's how tall the cone is. Surface area formula is given to you. The volume formula, that, again, maybe there's a relationship. My cone fits inside the cylinder. They have the same base and they have the same height. So do they have a similar relationship in their volumes? So again, if we fill up, how many cones does it take to equal one cylinder? What is your guess? So there's one. There's two. Will a third cone equal one cylinder? Yes, it does. So if you flip in your workbook to the following page, how does the volume of a cone compare to the volume of a cylinder with an identical base and height? The volume of a cone is 1/3 the volume of the cylinder. So if we take a look at the rest of the page, we get into the surface area of a pyramid and a cone. The area of the base times the area of the triangular faces for a pyramid. For a cone, the area of the base and the area of that curved surface. Because when we take a cone and we calculate or we draw out its net, into my tickle trunk here, here's a cone. The net of that cone, there's my circle, and then there's the curved surface. And this curved surface is equal to pi times r times s. And like I said, the proof for this is out of our math league in the grade 10 level. Volume. The volume of a pyramid is 1/3 the volume of a prism. Remember, the volume of a prism is the area of the base times the height. A cone is 1/3 the volume of a cylinder, which in this case, its base was a circle, so I get pi r squared times h. So let's get into some examples. The Great Pyramid of Giza is considered to be one of the 7 wonders of the ancient world. It is approximately 147 meters tall and has a square base with sides measuring approximately 440 meters. Make a sketch of the pyramid and calculate the volume to the nearest cubic meter. So a pyramid has a square base. Now I know this doesn't look like it's square, so we put in the measurements. If it's a pyramid, to meet at some apex. There's my pyramid. It has a height, that's the height, of 147 meters. So to calculate its volume, that will be 1/3 the area of the base times the height of the pyramid. The base is a square that measures 440 by 440, and the height is 147. So when I put this in my calculator, I can go 440 times 440 times 147. Then I can divide the answer by 3, or I can multiply it by 1/3. Either way, I get 9,486,400 cubic meters. That's the volume. Part B says make a sketch of the net and calculate the surface area. Explain why the base is not included in the surface area. So first of all, let's draw the net. The net of a pyramid, again, into my little pickle trunk. Here's my pyramid. The net is a base with triangles leading off of it. So the base is my square, measures 440 by 440. Now, I need to figure out what the slant height is of my triangles, because I don't have it. The measurement that I was given of my pyramid was from the tip to the center of the triangle. That was my 147. So imagine this. Here's my pyramid. There's my height. And if I grab another pen, what do I have right here? Between the blue pen, the red pen, and this side here, which would be my slant height side, I have a right triangle. This is my slant side. This is my height of 147. And this measurement right here, this is halfway in my base to the outside edge. Half of 440, which becomes 220. So to calculate my slant height, a squared plus b squared equals c squared. So s squared equals 147 squared plus 220 squared. Then I have to take the square root of that answer. So that answer is 70,009. Take the square root of that, and I get 264.59, and it goes on. So now when I go to calculate the surface area, I'm going to calculate the surface area of the 4 triangles. So it becomes 4 times base, which is 440, times slant height, which we just calculated as being 264.59, divided by 2. So if you put that into your calculator, what you get is 232,841 square meters. And finally, to answer the question, why is the base not included? The base is not exposed. If I tried to paint the Pyramid of Giza, probably get into a lot of trouble. But if I tried to paint it, I wouldn't be able to paint the base. Therefore, it's not included when I figure out the surface area. Continuing on to class example number 2. A cone-shaped container has a height of 15 centimeters and a base diameter of 16 centimeters. Determine its volume and surface area to 1 decimal place. So if I was to just sketch this out, there's my cone. Has a height of 15. There's my height of 15 and a base diameter of 16. So if the diameter is 16, that means that the radius will be equal to, that's right, 8. So now if I calculate the volume is the area of the base, the volume of a cone is 1/3 the area of the base times the height. The area of the base being the circle. So pi times 8 squared times 15. So 1/3 times pi times 8 squared times 15 equals 1,005 3/10 of a cubic centimeter. Surface area. Surface area formula is one circle, pi r squared, plus that curved surface, pi rs. Don't worry about memorizing the formula because you're given the formula. So I start to fill this out. Pi r is 8. S refers to slant height. So if I go back to my drawing here, I don't have slant height. This is slant height. I have vertical height. What did I just draw? Another right triangle, which now means, again, I can use Pythagoras' theorem. So we're going to do that in red over here. There's my slant height. This is 8, and this is 15. So S squared would equal 15 squared plus 8 squared. So that becomes 225 plus 64, which is 289. The square root of 289 is 17. So now I can put in S being 17. Put that into my calculator. My calculator should be able to do the order of operations. I should be able to type it in exactly how I see it. Press pause and try to do that. You should end up with an answer of 628 3/10 of a square centimeter. I'm going to skip class example number 3, and we are going to go to class example number 4. Two cones have radii of equal length. The first cone has a height of 5 and a volume of 10. State the volume of the second cone if its height is 20 centimeters. So let's look at problem number 1. Two cones have radii of equal length, which means if they have equal length, their radii, that means that their diameters are equal as well, which means the area of their bases is the same. So when I look at my formulas, this is the formula of the first cone, and this is the formula for the second cone. The pi r squared for both is the same. The first cone has a height of 5 and a volume of 10. State the volume of the second cone if its height is 20. Well, 5 to 20. How many times more is that? That's 4 times greater. So if the length is 4 times greater, the impact that it will have on the volume is to make the volume 4 times greater. So the volume would be 40 cubic centimeters. This 1/3, because it's in both equations, kind of cancels itself out. Don't have to worry about it. Problem number 2. Oh, I guess I should probably finish drawing my cones. One cone is 5, the other cone is 20. There we go. Second problem. 2 cones have the same height. The first cone has a radius of 5 and a volume of 10. State the volume of the second cone if its radius is 20. So the way that this is going to look visually, if this is my first cone, my second cone has the same height, but the radius is larger. The radius here is 5. The radius here is 20. So again, if I look at my 2 formulas, the volume of the first cone will be 1/3 pi times r, which is 5 squared times h. The second cone is 1/3 times pi times 20 squared times h. That equals h times h. This gives me 25. 20 squared gives me 400. How many times greater is 400 compared to 25? It is, figure it out, 16 times greater. That means that the volume will be 16 times more. So the volume will be 160 cubic centimeters. And again, 5 times 4 is 20, but because these were being squared, square the 4, what do you get? You get 16. So the questions that I would like you to work on for this class, 4, 5, 6, 8, 9, 12, 13, 14, and 15.